They want us to use this to approximate the amount of water in the tub at 3.5. So we would say it's best to label it like this. W of 3.5. You're going to use a squiggly equal sign because this is a tangent line approximation. It's not the exact value. 0.904. We'll do 3.5 minus 3 plus 2.5. And it really might be a good idea to use that, like, even though I wrote 0.904, to use this value right here that's in the calculator. So we're multiplying it by, that's just going to be 0.5 plus 2. Oh wait, that didn't work. Answer times 0.5 plus 2.5. And I'm getting 2.952. There as my approximation. So that would be my answer here. So, at t equals 3.5 hours, it is hours, isn't it? Minutes, sorry, it's minutes. There is approximately 2.952 cubic feet of water in the tub. Okay, questions? All right, let's pause here. I want to do something because we know more than we knew when you were originally supposed to be asked to do this problem. It's not a bad thing that we're kind of off on our FRQs. We're like a few weeks behind on our FRQs, so we're going back and doing older stuff. It's not necessarily a bad thing because it kind of keeps us thinking about things we've done before. But we know an even more precise way to solve this problem now, right? So this is not what you do for A. It's not part of this problem. You don't want to do this on the FRQ. I just want you to think about it. We could find the exact value for this, right? So there's another way that we know now, that is what we were looking at yesterday that we could do. So if I'm looking for W of 3.5, I know W of 3, right? I know my starting amount. I know at W of 3, I've got 2.5 cubic feet. So if I want the exact amount, if I want to figure out how much I have at 3.5, what could I do? How can I find how much the amount of water changed from 3 to 3.5? Yes, I could integrate, because f of t is the derivative of w, right? So I could integrate from 3 to 3.5 f of t dt. So if I did that on the calculator, W of 3 is 2.5, and then if I integrate y1 of x, comma 3, comma 3.5, I should have hit that green button. I get 0.447. So if I add that to 2.5, I get 2.947. That would be a more precise, like that would be the actual amount. Whereas this is a tangent line approximation. But you can see, because we're using the tangent line really close to the point where we had the tangent line, these are pretty close to each other, right? But this is not what you do for this problem. I just wanted to point that out. I'm going to erase it now. And we're going to talk more about doing problems like that, so you don't have to be terribly familiar with that. You won't see it yet. All right. All right, so we are now supposed to find W double prime of 8. And using correct units, we are to interpret the meaning of W double prime. It's hard to say. Of 8 in context of the problem. So now we are looking at the time being 8. Is the tank leaking at time equals 8? It is, right? So what we want to start with here is W prime of T is going to equal F of T, this is the rate that water is going into the tank, minus L of T, which is the rate at which the tank is leaking. So if we take the derivative of W prime to get W double prime, second derivative of W, how do we take that derivative? Just with the symbols I've got here, not the actual derivatives of those functions. F prime of T minus L prime of T. So W double prime of 8 would be F single prime of 8 minus L prime of 8. So let's look at the most efficient way to do this in the calculator. First, let's go back to y equals. Let's put L in y2. So we got 0.03 times 2x minus x squared minus 75. So you want to double check. Oh, mine's wrong. I put 2 instead of 20. Let me fix that. That, I think, looks better. Okay, so you'll make the danger of using y1 and y2 is that you might have something in y1 and y2 wrong, and that causes you to miss it. So double check that you have those right. You run that same danger if you're typing it into the calculator without using y1 and y2. So I would not really call it an increased risk, but it is really important that these are in right, because like where I had that 2x, that would have made all my answers wrong there for that. So we just want the derivative of f, which is our y1, at 8 minus the derivative of L, which is our y2, at 8. So we're going to differentiate y1 of x, comma x. Now, if I just type this in, it might give me the derivative. I'm not 100% sure. But I don't care about what the derivative is. I just want to know what it is at 8, right? So I'm going to go ahead and put such that x equals 8 behind this. Okay? And I'm going to go ahead and hit enter. Then I'm going to hit the green button and hit enter like I should have the first time. So, What I did, that happens to me, I went to second, 6, which is memory, did F1 reset, and then all memory. So, I think it should work. Try it now. Even though you're going to have to probably put it back in line 1, line 2, it might have cleared it out. Okay. So, I'm getting my W double prime of 8 is going to be negative 0.06273 minus, I need to do the same thing for y2. You can do it all in one step if you want. Sometimes I just get afraid that I've not typed things in right if I do too much at one time. Differentiate y2 of x, comma x, close your parentheses, such that x equals 8. Got 0.12. Are you guys getting the same thing?
I got 1.08.
Okay, you got the. Okay. Yeah, if you type it all in at one time, that is fine. Whatever. I get a little nervous when I'm typing lots of things in that I might have messed it up, so sometimes I do it piece by piece. The more you can type in at once, the better. It's all, these calculators almost give you just a teensy bit of like programming experience, but particularly with your parentheses, like if you don't have those right, it won't compute. Now it obviously is not exactly programming, but it gives you a little bit. Okay. Now we have to decide what in the world that means. Okay. W prime is the rate the water, and it's the rate the amount of water changes, right? So you've got water added to the tank and leaking from the tank. So it could be going up or down depending on whether you're adding it faster than it's leaking or not. But this is W prime is your rate that the water is changing. So we are looking at W double prime. So it's the rate that the rate is changing. So we would say at t equals 8 minutes, the rate of change of the amount of water in the tank is, since we have a negative, I'm going to say is decreasing at a rate of, so we've got the rate of change in the amount of water decreasing at a rate, so you got a rate of a rate here. Rate of 0.18273 units. It is feet cubed per minute, or you can do per minute squared. Because if you think about W prime, like if you think about that graph, you'd have minutes here, and your rate would be in cubic feet per minute. So when we take a derivative, we're taking our change in y over our change in x. So it's our rate for our y-axis divided by our rate for our x-axis, which would be cubic feet per minute times 1 over minutes, giving you cubic feet per minute, or cubic feet per minute squared. Okay, notice that I did not put a negative with this. That is because I used the word decreasing. This is the preferred way to write this. You say decreasing, you do not put the negative here. I think you can get by with is changing at a rate of negative 0.18273. What you cannot do is decreasing at a rate of negative, because if you say decreasing and then use a negative, they cancel each other out. Okay, we good here? All right, is there a time t from 5 to 10 at which the rate of change of the volume of water in the tub changes from positive to negative? Give a reason for your answer. So, what do you guys think? You can, let's see, hold on, let me think. Rate of change changes from positive to negative. I don't think we need that here. So it's asking us about the rate of change of volume of water in the tub. The rate of change of the volume of water in the tub is W prime of T. Right? It's the rate, because W gives us the amount of water in the tub, so W prime is the rate of change of the amount of water in the tub. And so that is from 5 to 10, it is F of T minus L of T. You don't necessarily have to write this because you already wrote it earlier. Okay. We want to know if this ever switches from positive to negative. First of all, from 0 to 5, is the value positive or is it negative? It's positive. Why is it positive? The water's not leaking. It's only being added to the tank, right? So we know that this is right here. Let me use a different color. This is rate that the water is added, and this is the rate that the water leaks. So, what condition do you have if that rate is positive? F of T is greater than L of T. You're adding water to the tank faster than the water is leaking, right? So if you have just a little tiny hole in the tank, a little bit's leaking out, but you're adding water faster, it's still going to fill up the tank, right? What happens if that, if this rate is negative? L of T is greater. You're filling up the tank, but it's leaking out faster than you can fill it up, right? So, what would we be looking at? Where would it switch from positive to negative? What would be the point where it would switch from positive to negative? Where they switch, right? So it'd be the point where they're equal to each other, right? So how could we find that? We could use the solve feature on the calculator. We do have arctan, which makes me a little bit nervous that we might freeze our calculator, but we can try it. So we want to know where F of And whenever you're doing things in the calculator, like whatever you're doing in the calculator, write down what you're doing. You don't have to write the details of what you're doing, but what we're getting ready to do is we're getting ready to see where f of t equals L of t. That's what we're trying to do on the calculator. So you're going to write that down so they know this is what you're trying to do. You don't have to write out the equations. You don't have to show steps for solving. You just need to write that down. And so let's see if the solve feature will work, because I like it better. Solve y1 of x equals y2 of x, comma x. Cross your fingers. Come on, you can do it. We may have broken the calculator. Anybody got it to work on theirs yet? Yours worked? Okay, maybe it's coming around. Maybe. What did you get, Maddox? Okay, so the 14, do we need to use it? No, because it's not between 5 and 10. So although it is a solution to this, oh look, there it goes. Okay, it took it a little while, but it did work. Now it's still going to be helpful for me to look at my graph here. My window's probably not great, because I need, maybe it'll work. Oh. Nope, I just barely missed it. Alright, let's go from 0 to 10 and graph that. Alright, so y1 is the rate that the water is. Okay, so y1, the one that graphed first, that was my rate that the water is being added to the tank. Then the second one, that's our leaking rate. So we could say for 5 less than t less than 8.149, f of t is greater than L of t, so W prime of t is positive. Right, so because the rate that the tank is filling up is bigger than the rate that it's leaking, then our rate of overall change is going to be positive there. Then we could say for 8.149 less than t less than 10, L of t is greater than f of t, so W prime of t is negative. And then I would restate what the question asks. Therefore, at t equals 8.149, the rate of change of the volume of water in the tub changes from positive to negative. I'm running out of room and I'm using plus and minuses there, which is not, I've told you not to do that, but I just did. It would be preferred to write those words out. this one does actually have a related rate in Part D, I guess. The first part, in a way, these are related rates. You're like a rate in, rate out sort of problem, but it's not a related rate like you had to take the derivative with respect to time. But Part D is a related rate problem. So the tub is in the shape of a rectangular box that is 0.5 feet wide, 4 feet long, and 3 feet deep. What is the rate of change of the depth of the water in the tub at time t equals 6? So, we have to think about our tank here. And it tells us that it's 0.5 feet wide, 4 feet long, and then 3 feet deep. However, one of those numbers we're not going to use. Which one is it? Whenever we think about the water filling up here, so we got our water level here, right? So, well, I don't know how to like make that look 3D-ish, I guess, like this. That's even better. Anyway, so when I think about the water, not the tub itself, the length of that water is 4, the width is 0.5, but the depth is going to change as you fill it up or it leaks out, right? So,
I found this on the web.
She's always listening to me. So, the volume of that water, not of the whole tub, but of the water, is going to be 4 times 0.5 times, I'm going to call the depth D there. So we're calling that depth right there, D. So it's asking for the rate of change of the depth. What is that asking for? Like what symbol are we looking for? DD, DT. So we're going to take, well, first we're going to do this. We're going to do V equals 2D, because that just makes it a little easier to deal with. We're going to take the derivative of that with respect to t. So dV dt equals, this is just going to be 2dd dt. Okay? dt is what it's asking for. That's what I'm trying to find, so I'm not replacing it. dV dt. What is dV dt whenever t equals 6? How would I find that? It is W prime of 6, right? Because that's the rate of change of the volume of water. dV dt is the rate of change of the volume of water. So it's W prime of 6, which is F of 6 minus L of 6, which, if we go back over to our calculator, we can do y1 of, oh wait, we gotta go back to the home screen. We can do y1 of 6 minus y2 of 6. You don't have to take the derivative because W prime is just, because F and L are rates, they're kind of like already derivatives, right? So we don't have to take the derivative here. We're just subtracting those. So we'll get 0.50051. So that goes over here. 0.500581 is going to equal D2 times dd dt. we're just going to divide both sides by 2, and our dt is going to be 0.250291. You can round that off to 0.250. There's something about rounding that off to 0.250 which makes it look like it's only 2 decimal places that I just feel like I need to keep those extra. You can always keep extra, it doesn't hurt on that. And so we could say at t equals 6, the rate of change of the depth of the water in the tub is 0.250291. What are the units on that? Cubic feet per minute. So it is a rate of change of the amount of water. Oh, you're right. You're right. Yeah, you're right. It's depth. I was on volume. You're exactly right. Feet per minute. Thank you, Connor. You guys understand that difference between the cubic feet and the feet for this one? Cubic feet would be volume. That's why we were using cubic feet up here. This is depth. Depth is just measured in feet, not cubic feet. That was probably the best one to pick. I don't think 2 is as bad as this one. Okay, questions? All right, we will have our FRQ quiz on Monday. So that assignment will be due on Monday. So you will make sure you get the other 2 done. I will make sure that I get the that I meant to mention yesterday, but I was going too quickly there at the end. Let's talk about why you have to do something different, because a lot of times it does not become obvious why you need to use a natural log for these. So if I see a problem like the integral of 2 over x dx, it may not immediately stand out to us that we can't just use the power rule on that. So let's look at what happens if we try to use the power rule. This would be 2x to the negative 1 dx. And here is why we cannot just use the power rule on that. If we try, what's our power rule tell us to do to the exponent? Add 1. That gives me x to the 0, which is okay. You can have x to the 0. But then what do I have to do with that? Divide by that new exponent. Can you do 2 divided by 0? You cannot. So this will not work because you're getting something that's undefined. That can't be the answer to the problem. So sometimes it's not terribly obvious what you were supposed to do with those because they just seem like they are more power rule problems. But if you find yourself having to divide by 0, that should be an alarm to your brain that you should have used a natural log instead for that. Now, be careful also, though, because if I have something like 3 over x squared dx, is this a natural log? It is not, because it would be 3x to the negative 2 dx. So I would increase my exponent by 1, which would give me negative 1. I'd have 3 divided by negative 1, put a plus c on the end. So I would just have negative 3 over x plus c. So it's only when you just have an x in the denominator that you end up with that natural log. If it's x squared, x cubed, x to the 1/2, any other power besides 1, you will just use the power rule for that. Okay, questions on those? There is one more we need to look at. It is super duper simple. And that is e to the x. So we will have to do like some chain rule sort of stuff when we get to integration by substitution. But right now, all we're doing is we are taking the integral of e to the x, which is going to be the easiest that we have to deal with, because what is the derivative of e to the x? E to the x. So if we integrate e to the x, what will we get? E to the x plus c if it is an indefinite integral. These two examples are definite integrals, so you don't have to worry about that. So, for example 5 here, I've got e to the x over 5. It kind of looks like you've got some sort of crazy fraction there, but this is really just like 1/5 times e to the x. So you could even think of it like this. You could like pull that 1/5 out front. You got -2 to 3 of e to the x dx. So when you integrate e to the x, you just get e to the x, and you want to evaluate that from -2 to 3. So you will have 1/5. That 1/5 you can kind of distribute it, or you can just keep it out front. I think I'll keep it out front. We'll have e to the 3rd minus e to the -2. And you can't really put those together. You might could do like some common denominator sort of stuff. I think I'll probably just leave it like it is. Okay, questions? Okay, 6 puts a few things together because we have some trig and we have e's for this. Yes. Definite integrals, you do not have to put a plus c because they will cancel each other out. If this did not have that -2 and that 3 right there, then we would just get 1/5 e to the x plus c. You would need it if it was an indefinite integral. But since these are definite, you do not have to put the plus c. Okay? For this last one, what is the integral of cosine x? It is sine x. Just regular sine x. When we take the derivative of cosine, it's negative sine x. But when we integrate, we just get positive sine x. So we're going to have 3 sine x. And then what is the integral of 5e to the x? 5e to the x. And we are going to evaluate this from 0 to pi over 2. So when we're evaluating this, we're going to have 3 sine of pi over 2 minus 5e to the pi over 2 minus, and then we're going to plug in the 0. 3 sine 0 minus 5e to the 0. Alright, unit circle never goes away. Sine of pi over 2. This would be at 0, 1. What's sine of pi over 2? 1. So we got 3 times 1 minus, you really can't do anything with that 5e to the pi over 2 unless this was a calculator active problem, which it is not. So we would just have to leave it 5e to the pi over 2. What is sine of 0? It's 0. So we're going to get 3 times 0 minus 5. What is e to the 0? 1. So we end up with 3 minus 5e to the pi over 2 minus -5, which is going to become a plus 5. So we would want to put those together and get 8 minus 5e to the pi over 2. I don't like problems that still have e's and pi's in their answer, but unless this was calculator active, that would be the best you could do. Okay, questions? All right, let's see. We go to Canvas for your assignment. All right, today, where are we at? You guys are going to be on page 328, 5 through 29 odd, 37, 47, 48. Right up here bigger. So page 328, 5 through 29 odd, 37, 47, 48.